Ruby Community Conference done by Visuality, Ruby on Rails Experts Agency, presents Aaron Patterson, Speeding Up Class New. Enjoy.
Stage is yours. Good luck. I know that you will manage it. So.
All right. Hello, everyone. Hello. Happy Friday, everyone. Yes. I think it's Friday. I'm still a little bit jet lagged. I think it's Friday. I want to start off by saying thank you to the organizers. Thank you so much for having me here. Please clap for them. Yes. I am so happy to be here again. What? Yes, it's true. I spoke in this auditorium on this very stage at Railsbury in 2012. That's a photo of me right there. I couldn't believe it. Of course, it is the year 2025, and I am absolutely much older. I am much better looking, and I'm much smarter now. Though I want to give an example of how much smarter I am today than I was back then. This is a beer I was having in Warsaw. So my wife and I came to Warsaw, and then we traveled down here. But the first night we were out, we decided to go out and get some food and have a beer. So I decided to have this beer, and I took a photo of it just to remember, because I'm trying to take more photos of my food. But I want you to notice something, which is just how close this candle is to to these napkins. A few minutes later, Abby says to me, "It feels quite warm in here." And we look down, and all of these napkins were on fire. So the whole thing, it all completely burned up. We had to call the waitress and say, "Oh my gosh, this is all burning," but they took care of it. It was okay. But yes, so maybe I'm not smarter these days. So today I'm going to be talking about speeding up class new. I'm really excited to talk about this. It's something I've been working on for a very, very long time. And if you've seen any of my presentations in maybe the past year or two, most of that work is basically just so that I can do this, which I am really excited to share with you today. My name is Aaron Patterson. I am on the Ruby core team. I am also on the Rails core team, and I want you to know that I attended the workshops this morning, and it was the very first time I had written any Turbo. But please don't tell anybody. That's the case, but it is true. I am a professional Rubyist since 2008. I've been doing it professionally. I put that in quotes. It's when I got my first job doing Ruby. And I love Ruby. This is a fact. I love Ruby. I love programming Ruby, and I want people to write as much Ruby as possible. So that's basically what I try to do on a day-to-day basis, is figure out how can we get people to write more Ruby. I recently published a blog post about writing more Ruby. I hope you check this out. It's really fun. I'm really happy about the work I did for this post as well. But I love Ruby because it's easy to read. It's such an easy to read language. It's also very, very easy to write. And I love Ruby because it brings me joy. This is I made that. That's me. One thing that's interesting about Ruby is YJIT can optimize Ruby, but YJIT can't optimize C. So this is why I try to encourage people to write as much Ruby as possible. Actually, how many people here are using YJIT? Okay, quite a few. There should be more. You just need to add --YJIT. But YJIT can't optimize C, so I want people to write as much Ruby as possible. And in fact, if you look at newer versions of Ruby, if you go look in the source code of newer versions of Ruby, you'll see Ruby 3.4 has even more Ruby in it than it did before. You'll see that some of the methods are actually implemented in Ruby now. So for example, numeric down to. This is what numeric down to looks like in Ruby. I'll admit that it's a very weird looking Ruby, but it is Ruby code, and we're trying to implement more and more things in Ruby. So in this presentation, I want to explore a few different things. First off, can Ruby be faster than C? And the answer is yes. But of course, we have to ask, like, how can that be? Like, how can Ruby be faster than C? Another thing is, like, can we write class new in Ruby? Like, can we do that? And the answer is yes, of course, but is it fast enough? Like, if we rewrote it in Ruby, is it fast enough? I want to study the implementation of class new. We can't really speed up some code if we don't understand how it works, so we're going to go through the existing implementation and try to understand it. Along the way, we're going to be looking at how inline caches work, what inline caches are, and how they speed up our programs. We're also going to study calling conventions, what they are, and their impact on our method calls, why we have to care about these things. After that, we're going to take a look at rewriting class new in Ruby, and then we're going to do some performance testing on it. So why would we target this? Like, why class.new? Why is this something, or class pound new? Why is this something that I want to target? One of the reasons is it's implemented in C, and as I said earlier, I really want stuff to be written in Ruby. I want more Ruby, more things to be written in Ruby. The other reason I wanted to target this method is that it's very popular. Like, this is a method that we call a lot, I think. People here, you make new objects, right? Yes, this is not a trick question. You create new objects. You're calling things like user new or your business object new. That's a thing that we do. I mean, think about it. Like, how many objects are we making on our Rails requests? Like, I don't know, tens of objects? At least 10, right? maybe 100,000 objects. Too many objects. 500,000 objects. Are you anyone up to 1 million objects? Anyone? What is that? All of the objects. Yes, you're doing all the objects. So the point is, I wanted to target this method because it's something that we use. We use it a lot. It's something we use. The other thing is, it doesn't actually do very much. Like, when we create a new object, this class new method doesn't do that much. So, I mean, I am very lazy. So if I can do a little bit of work that has a large impact, that makes me happy. So that's why I wanted to target this. So let's take a look at the current class new implementation and see how it works. Now, when I'm like investigating some code, one thing that I like to do is I like to before I go dive into the code, I like to imagine how the code might work. So I think about what it does from a high level, and then try to think like, okay, if I were to implement this method, or if I were to implement this code, how might I go about implementing it? Like, what would I do? And that gives me a kind of a good idea of things that I should be looking for as I'm perusing the code base. Now, class.new, if you think about it, all it really does is it allocates an instance. We create a new instance of an object. Then we pass our parameters to initialize. And then finally, we return the instance of that object. So if we were to write it out in Ruby, and this is not the final Ruby implementation, we're just gonna like kind of map it out in our brains. If we were to write it out in Ruby, it might look something like this. Like, this is, actually, I think this is very close to the first implementation I did. Like, this is the first implementation I did. And it's actually buggy. Let's see if we can figure out why it's buggy. So the first thing that we do here is we allocate a new instance. So we call allocate. That works great. Get a new instance. Then we pass all the parameters that came to new. We have to pass those to initialize, so we do this here. But this is actually where we've made our mistake. The issue is that, of course, we all know methods return the very last thing that happened in the method. So what's going to happen here? Initialize, it's going to return what? Foo, yes, exactly. So we get the wrong value back. We expected to get an instance of foo, but no, we get this :hello here. It's not going to work correctly. So really, what our second, less buggy implementation looks like is something like this, where we have to first allocate our object. We'll store the object into a local variable. We'll pass our parameters to initialize, and then finally we'll get our local variable again, and then we will return that back to the caller. So this is a bit more accurate of what the implementation looks like. Now there's a couple things to notice here. We have inside our implementation of new, we have two method calls here. So there's two method calls, one to allocate and one to initialize, which means we may have two inline caches going on here. So this is kind of why we're thinking about inline caches. The other thing is we're taking the parameters that were passed to new, and then we're passing those down into initialize. And this is kind of why we have to think, we're calling methods, so we kind of have to think about calling conventions in this case. So that's why, this is kind of driving why I want to talk about inline caches and calling conventions. So let's take a look at the actual implementation in C. This is the actual implementation of class new, the current implementation. I put an example down here in Ruby, of course, at the bottom, and we call from here, this foo new calls into the C code, and I kind of want to map out what this does here. So on the very right, we have that class variable. That is equal to foo, so that's what that equals. So when we call this method, class is equal to foo. The allocation of the new instance happens right here. We just call this C function. That allocates the new instance of our class. And all that does, there's actually no Ruby method call here. All that does is call into the garbage collector and say, hey, give me a new instance of this thing. It gives back a new instance of the thing. And then finally, we have here, in this value, argv, that's an array of our parameters that go to new. So we take that array of parameters that go to new, and we'll pass that to initialize. So this function here in the middle, rbobj call init kw, that's where we actually call initialize on your object. So we'll take argv, we pass it down into that function. That function eventually calls initialize on our implementation of foo. And then finally, at the end of this function, we return obj. So it's very, very similar to the Ruby code that we wrote. So to recap, like if we want to recap what this did, we start off in Ruby, which is calling into C right here, and then we call from C back into Ruby right here. So if we think about this, one problem we have is every time we cross these language barriers, we have to transition between calling conventions. So we have to say like, hey, I'm using Ruby, but I need to call into a C function. I have to conform to the C function's calling convention. And then when C calls back into Ruby, we have to do that in the opposite direction. So if we can stay in one language, we might be able to speed things up. So what I'm trying to say here is like, let's say we have two bits of code here. They do about the same thing, but one of them switches between Ruby and C, and the other one stays in Ruby. So it may not be that our Ruby code is faster than the C code, but when we execute the one on the left-hand side, it might take a little bit longer to cross that language barrier as it executes, whereas we might be able to get higher speeds in this side, on the Ruby side, if we stay inside Ruby. So to kind of like map this out a little bit more, like let's say we have time going across the bottom like that. If we were to convert this middle part that's in C into Ruby, it might be that that Ruby code is slower than the C code, but transitioning between Ruby code is faster. So when we measure the overall performance of this code, what we really want to do is we want to look at the system as a whole. Like we want to measure these arrows in addition to how long it takes to for that code to execute. So this is one way that we can make Ruby faster than C. So it's not necessarily that the Ruby code is faster, it's just that our overall time is lower because our calling conventions are better. So where is our time being spent? Of course, this is always an important question to ask when you're trying to speed something up. You can't speed it up if you don't know where your time is spent. So the size of these arrows here in the middle is going to be impacted by our calling convention, and that's why we need to look at calling conventions. Additionally, we're spending time calling methods inside this code, and those touch inline caches. So when we think about this, there's two major factors that are impacting our time, and that's the calling convention and also method lookup. So that's why I want to talk about inline caches. Inline caches, all they do is they make our method lookups faster. So let's discuss inline caches. We're going to discuss calling conventions later, but let's look at inline caches. So inline caches is simply a way that we can speed up method lookup. So for example, let's say we have some code like this. We're calling inside the foo class from bar, we call baz. But the question is, like, where is the baz method? Like, where is it located? When we look at this code, you and I can see, like, right there, it's defined on foo. Like, we see it right there. But computers aren't necessarily as smart as we are, though ChatGPT is catching up with me. So they can't just see that it's defined right there necessarily. They have to go searching for it. And the algorithm for searching for it looks something like this. Essentially what it does is it says, hey, is the method defined on this class? If not, I'm going to go look at an ancestor class and see if the method is defined there. If it's not defined there, it's going to go up another one, and it's going to keep looking for these. It's going to keep going up until it hits the very top, and if it couldn't find the method, of course, you get an error. But we have kind of a problem, and that's that this method lookup can be linear. So, well, it is linear. So in this case, like, hey, you'd say, I'm looking for baz, and if you have tons and tons of ancestor classes in there, it's going to take a while for it to find that method. So, like, how do we speed this up? What can we do about this? Well, we simply cache the method call, or not the call, we cache the method lookup. And I want you all to know here that this is not like a magical thing. I think when I started looking at programming languages at first, I was like, cache, what do you mean? How can we cache this? There's no memcache involved here. What is the deal? But it really is just a cache. It's just a cache like any of our other caches. Now, this cache, the receiver type, so the type of the receiver, that's our cache key. And the value of the cache is just the method entry itself. So in this case, like, the cache key is going to be foo, the class foo, and then the value is just going to be our method entry. And this cache is stored in line with the bytecode. So if we disassemble this bar method here, so let's take a look at the disassembled instructions. This is yarv bytecode here. And the cache is actually stored right here next to that send. So it's stored here in this place. I know it doesn't look like a cache, and you can't really print out the cache, but that's like where it is, really. It's stored in line with the bytecode, and that's kind of why we call it an inline cache. So I want to show an object graph of these inline caches. The object graph looks kind of like this, where we have class A down in the bottom right here. Class A owns an inline cache object, and that inline cache object points at the abaz method. So we have kind of a triangle there, and then we have the bar method itself pointing at the baz inline cache. Now, this cache is actually a weak reference, so it can be invalidated. It might point at something else later on. The other thing I want to point out is that these objects, they're actually all Ruby objects. All these are Ruby objects. The inline cache is a Ruby object. The method is a Ruby object. Of course, classes are Ruby objects, and the bar method is a Ruby object as well. But what's interesting is that some of these objects are lazily allocated. So the bar method and the baz method, those are allocated when you compile the code. So as soon as you run it, those get allocated. Now, the baz inline cache, that's created lazily. And we can actually see that. So if we measure allocations, like let's say we're going to measure some allocations, we call a method, and you'll see that the first time we call that method, it actually allocates stuff, even though it's just an empty method. It doesn't do anything. So it'll allocate objects the first time that we run it. And this is kind of why warm-ups are important for doing benchmarking work, because we'll see these allocations unless we warm up. So the point here is the Ruby VM itself can have caches that it needs to populate. Oh, goodness, I should move more quickly. One thing about this object graph is that this inline cache can only hold one reference at a time. Our cache size is 1. It is only 1. And that means it only holds a reference to this baz inline cache. What that means is, like, we can invalidate it fairly easily. So here's an example. We have this run it method. Run it, all it does is it takes an object and it turns around and calls a method on that. So let's imagine the very first time we call the run it method. When we call that, It's going to say, okay, I need to look up the bar method on obj. Well, that belongs to the class A. I'm going to keep a reference to the inline cache for the bar method, and we have an inline cache there. Now remember, the class itself is the key, so the class of the receiver is the key. So in this case, we'll run it with B, and all of a sudden our cache is invalidated, and we have to go look it up again. So we only have one reference there. Here's some examples of our cache hits and misses. So we can see in this first chunk of code, when we call run it with an instance of A, the first time we call it, there's a miss, and then subsequent times, it's hits. But if we switch between A and B, then we always get a miss. So what's kind of interesting about this is it means we can measure the impact of these inline caches. So we can actually write a benchmark that says, like, hey, I want to know how fast does an inline cache make my code. So I did that exactly. We have two benchmarks here. The top one runs run it, but it always runs it with the same instance. So it always runs it with A. The other one alternates between A and B. So our first case, it's always hitting inline caches. Our second case is always missing inline caches. So we can, if we take the difference between those, we can see what the impact on inline caches are. So if we run the benchmark, we'll see that, in fact, inline cache misses are 40% slower. So if we never hit, it's 40% slower. What this means is that inline caches are very important for performance. Now, all the stuff that I've been talking about so far, all the things that we've been reviewing, is all Ruby code. Like, we've only been looking at Ruby code, and you may be thinking to yourself, well, Aaron, class new. It is written in C. What does this have to do with anything? But the thing is, like, we actually have these inline caches in C too. Like, if C doesn't have inline caches, wouldn't it be slower than Ruby? And we know that's not the case. So I want to dive a bit more into the implementation here. So as we said earlier, we call this function rbobj call init kw, very easy method name to say. We're going to dive into that thing. So that thing, it's implemented like this. It's just these two lines of code. All it does really is it calls this rb fun call v kw, really another easy function to say. This function, all it does is it says, hey, I want to call a method. I'm going to call a method on a Ruby object. Which Ruby object am I going to call it on? We're going to call it on this Ruby object. What method are we going to call? We're going to call this method, the initialize method. And then we're going to pass parameters in argv and then some other information, but we don't need to worry about that. I'm going to paper over it. Don't worry about it. It's all good. So let's go look at that function. All it does is it turns around and calls rbcall. And basically, all it's doing is taking its parameters and turning around and calling rbcall with its parameters. Now, if we go look at rbcall, it just calls rbcall0. And it's just basically taking all those parameters and passing them down to rbcall0. Why is it called rbcall0? I don't know. I have no idea. You'd think the other one would be rbcall1. I don't know. So let's go look at rbcall0. This one's actually very complicated. This is where the actual work happens. And I've put it on the slide here, but I deleted a lot of the code, the stuff that we don't particularly care about for this presentation. Now, if we look in the center there, there's a thingy that says rbcall cache. It's very, very interesting. This is exactly the same data structure that the inline caches use. This is, I know it looks like C, but this is actually a Ruby object right here. So this call cache is a Ruby object. And we're dealing with the same data structures that the Ruby program is dealing with. So the question is, like, if Ruby methods store caches in bytecode, where do C functions store them? Now we're going to get into some really easy to read code here. That is the search method for the cache. Quite easy to read, but if you, that was a joke. It is not easy to read. If we look in the center here, really it's just accessing a global variable. It's looking this cache up inside of a global variable. Our next chunk of code is saying, like, is this cache good? If it's good, we'll return the cache. Otherwise, we'll take a slow path search. So our C methods that call into Ruby methods have method caches. They do. It's just stored in a global variable rather than inline like our Ruby code has done. And the cache entries are limited by this global table size. So there's only a certain number of global caches that can be stored. All right, let's move on to calling conventions. I think we've looked at inline caches enough. We've learned as much as we need to in order to re-implement class new. So let's talk about calling conventions now. What the heck is a calling convention? A calling convention simply is a convention for calling methods. Yes. So easy, so easy. No, a calling convention is a way for us to connect methods. So the calling convention defines where parameters and return values are stored. So all it's saying is like, hey, we're going to store the arguments to this method in a certain place. And then the caller is like, hey, I know my parameters are going to be stored in a certain place. So when I need to read the parameters, I know where they'll be. So the callee is like, okay, I know where they'll be. And the caller is like, okay, I'm going to put them in these certain places. And it's the same deal with the return value. So the return value is, the callee is like, I'm going to put the return value in a certain place. And then the caller is like, I'm going to like read the return value from a certain place. And the nice thing about this is that when we compile methods, we don't need to know anything about that method before we compile a method. So we compile the method body and we're like, well, you know, we're calling the bar method. We don't know where the bar method is, but it doesn't matter because as long as we've put all of our parameters in the correct location, we'll be able to call it and everything will work out just fine. The important thing is it's a way of simplifying our compiler. We're able to decouple our caller and our callee. So we decouple those two things so that the compilation process is much easier. And languages can define their own calling conventions. It's totally fine for them to do that. They can and do that, which means that the locations where we store parameters in Ruby are different than where we would store them in C, for example. So I want to look at the calling convention for C. I apologize, there's going to be assembly language in this presentation, but we're going to do it. When you compile a C program, the program is translated into machine code, and that machine code is run directly on your processor. Now, all processors are register-based, so we're going to take a look at how a register-based calling convention might work. So these machines work with a bank of registers, and these registers are just scratch spaces inside of your processor. So you can store a value in that scratch space temporarily. And the number of spaces is limited, like it's not infinite. You only have a certain number of them. And the machine code just manipulates each of these registers. So in this case, what we're doing is we're saying, hey, we're going to store, I'd like you to put the value 123 into the X0 register. So the processor does that. Then when you say, hey, I want you to move the value 456 into the X1 register, the processor does exactly that. And then our third instruction here, all it's doing is saying, hey, I'd like you to take the values from the X0 register and the X1 register, add them together, and put the results into the X0 register. So it does that exactly. And this is an example of assembly on ARM64, so all of your Macs are doing this. It's very, very similar on x86, basically the same concepts, just different verbs and different syntax. So the C calling convention is processor specific. It means that the calling convention for C is different depending on the type of processor that you use. And for our purposes today, it doesn't really matter what those differences are, but just know that they are different. And the example, as well as that the space you have is limited. And the example that we looked at, like I said, it's on ARch64, your ARM64 machines. On ARM64 machines, we have 31 general purpose registers, and all parameters are stored in register X0 through X6. So that is the calling convention. So we say, hey, when I'm calling a function, you can find all of the parameters for the function in each of these registers. And the return value is always going to be stored in the X0 register. So let's say, for example, we write some C code like this, where we take 3 parameters, we add them together, and we return it. So when the C compiler goes in and compiles this method, it says, okay, I know that I'm going to have to place 1, 2, and 3 in X0, X1, and X2. And then when we compile the add function, it says, I know I'm going to have to find A, B, and C in registers X0, X1, and X2. So then it can add all those together, and then when it's done adding them together, it just places those into x0 as the return value. Now I have a question for all of you. What if there are more than 7 parameters? This is an exercise that I will leave to you to investigate after we're done here today. Oh my goodness, let's move more quickly. If you want to mess around with ARM64 stuff, I wrote this gem, it's fun. You can write ARM64 machine code in your Ruby code. So if you do feel like you don't have enough machine code in your day-to-day jobs, do this. All right, so let's take a look at Ruby. Ruby is a stack-based virtual machine, meaning it manipulates a stack, and our stack is infinitely long. You can think of it as an infinitely long list. So for example, we have some code here that just adds 2 and 3. Our instructions will look like this. We'll push 3 on the stack, push 2 on the stack, push 3 on the stack. When we execute the add instruction, it'll pop 2 values and then push the return value on the stack. And finally, we'll return. And when we return, the return value is always the last value on the stack. When we return, there should always be 1 value on the stack, and that is our return value. Yes, great job, Aaron. So that is from the calling. Let's take a look at the calling convention of Ruby. First, we'll look from the caller's side. So foo, we're going to look from foo's side. Bar is the callee, so foo is our caller. And the YARV bytecode for foo is going to look like this. So we'll say, hey, we're going to push 5 on the stack, then we're going to push 7, then we're going to push 9, and then we're going to call bar. So when this happens, when we transfer control to our callee's function, we draw essentially a line here at the bottom of the stack. So we say, hey, we're going to draw a line right there. It doesn't actually happen in your computer. There's no line drawing. It's an imaginary line. So we draw this line in the stack, and what happens is the parameter values are all essentially negative offsets from that line. So it understands where to find parameters based on where that line has been drawn in the stack. So in this case, it treats, Ruby's VM actually treats locals and parameters as the same thing. So I know it says get local here, but it's using the same thing for parameters. It uses locals as parameters. So in this case, we'll say, hey, we're going to do get local -3, which corresponds to the value A. We're going to push that on the stack. Then we're going to do get local -2, which corresponds to B. Push that on the stack. We'll add the 2 together. It pops those values off, adds. Then we'll say, hey, we're going to get A, push that onto the stack, add those 2, pops them off. Then finally, we return, and our return value is the last value that's on the stack here, 21. Yeah, great job. I did it. All right. So one fun fact is that this calling convention is the same even when we use keyword arguments, and this will be a little bit important later. So if we convert this method to use keyword arguments, the callee still expects all of its parameters to be on the stack here in order. So we all know, like, you can call keyword arguments in any order that you want to. So what happens if we swap and put C there first? Like, what's going to go on there? Well, what actually happens is at the point that we call bar, when we do this call to bar, it'll actually go in and rearrange the stack so that the stack is in the correct order for the callee. It has to do this work. So that means that the Ruby VM is able to introspect onto the function that it's calling and reorder the parameters the way that it needs to be. And what this means in practice is that keyword arguments can be slower than positional arguments, but please do not change your code. If I see someone send a RuboCop performance cop because of this, I will personally get upset with you. So don't change your code. Because I feel like the reason I think it's really, really important you don't change your code is I think, like, we can probably come up with a way to make this faster in the future. So, like, don't worry about it. What's nice about this is it's all the same, like, this code is all the same on every platform. We don't have to worry about platforms. This stack-based VM works exactly the same on your x86 as it does on your ARM64 machine. There's no concepts of registers, but that being said, when we look from the C side, there's no concepts of keyword arguments or splats or defaults either. And because of this difference between these calling conventions, it means that when we try to call Ruby to C, we have this friction between the two languages. We have to do this conversion. And this conversion takes time. It also uses memory. And I want to show you an example of it using memory. So let's say we have this case here. We're doing a Ruby to Ruby call with keyword arguments. If we call this, we'll see, hey, there's no allocations. 0 allocations when we call this method. But let's say we call through C like this. So you would expect from the previous slide that I showed you, we would only have 1 allocation in this case. We would just have the allocation for foo. But that's not actually the case. We get 2 allocations in this case. And the reason is because of this mismatch in calling conventions. What ends up happening is, as we call from Ruby into C, we take these stack values, the values that we had on the stack, we convert those into a Ruby hash. They get converted into a Ruby hash because C does not understand these keyword arguments, it only understands positional arguments, so we turn it into a hash. Then, when C is calling back into Ruby, we have to say, oh, well, we have to convert these into stack elements again because that is the calling convention of Ruby. So we'll take that hash and turn it back into a stack in this particular case. So this is why we'll see extra allocations as we cross this language barrier. So let's fix this new implementation. We're going to rewrite. We're actually getting to the Ruby code of it all here. We're going to do this. We're going to do this. I think this might have been my first implementation. There is a problem here. Does anyone know what the problem is here with this code? This is a trick question. It's a trick question. I'll just tell you. Initialize. Fun fact: initialize is actually a private method. You can't do this. You'll get an error. Like if you run this, it'll say like, oh, you private method initialize call. Like you can't do that. It's really, really wild. Like imagine, when you're writing private methods, you got to put private there. Initialize is a special case where it's declared as private when your class is allocated. And there's a few other ones. This would be I think this would be a really good Ruby trivia question. Like what methods are private even though you don't declare them as private? Because I actually don't remember. I know this one in particular is, but there are others. So, okay, so we got to do something else. Here's our second implementation. We'll say, okay, well, we need to call it, well, we'll just use send. Okay, I'm just going to call send. This also doesn't work. Anyone know why this one is? This is not a trick question, I don't think, but it might be not obvious. It's not, okay, I'll tell you. Basic object doesn't have send. You can't call send on a basic object. So like if you try to do this, it'll be like can't do that. Okay. Getting kind of desperate here. We need to call a private method. Somehow we need to call that private method without using send. How might we do that? Don't worry, I'll tell you. The way that we do it is that we cheat. Because today we are all on the Ruby core team and we get to modify the internals of Ruby however we want to in order to achieve our master plan of calling a method without using send. So the way that we do it here is if you look at the instruction sequences, so like up here in initialize, we're calling a method. Everybody's done this before. You've called a method and you don't have a receiver, right? You don't do like self dot or blah dot or whatever. You just call a method. And if you look at the instruction sequences from methods like this, you'll notice something in particular down here. We have a send instruction. This send instruction, it has a special flag on it. So I'm going to run over here. These are flags. So all those are just flags that are on that particular method call. The fcall flag, what that means is, I want you to call this method. It's telling the virtual machine, it's saying, hey, I want you to call this method, but I don't want you to check the visibility of the method. Just call it. That's what I want you, just call the method. So we need that. That is what we need. But the issue is it only emits this instruction when there's no receiver, or if the receiver is literally the keyword self. So it has to be those two situations, but we don't have that situation here. We're calling it on something. So we end up with code that looks like this, where we have a method call right here, and what we really, really, really want is an fcall flag right there. We want that flag right there. So the way that I accomplish this is by using a new primitive, and what primitive is a bit of code that the Ruby compiler treats specially. So if you go look, actually you saw it earlier in these slides in the down to implementation, but there is a special class inside of Ruby called primitive that the Ruby compiler treats very specially. When it sees this, like a primitive.blah, it'll execute something special inside of the compiler, and it lets us run whatever we want to in that case. Like we can do weird tricks in that case. So I added a new primitive called send delegate. So you do primitive.send delegate, and what that does is it creates a send call, like a send instruction, but it adds that fcall flag to it. So it's saying, hey, I want you to call a method initialize on object, and I want you to pass triple dots, so all the parameters, but I also want it to be an fcall, so please ignore any visibility. So if we look at the instruction sequences from this, we'll see, hey, we've got a send now, but it's got our fcall flag. So we did it. We were able to do initialize without send. We did it. Yes. Yes. Implemented it. Oh no. We're not done. Don't clap yet. No. Unfortunately, the tests don't pass. Anyone know why? This is not a trick question, but it is so dumb. Like, you're gonna get mad. I guarantee all of you are gonna be upset. The reason it doesn't pass is because people can monkey patch allocate. Well, you can do that. There's a test. There's a test like this. It doesn't say ha 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 ha, but there is a test where you monkey patch allocate, and allocation will ignore it. So if you do foo.new, it'll just ignore that. It'll allocate your object. So what do? Well, we cheat, new primitive. Yeah, let's do it. Nice, new primitive. So I added a new primitive that's this one, RB class alloc2. Yeah, great name. All it does is it allocates a new object. It just allocates a new object. And what's cool, though, is it skips the method call. So we don't have to worry about method lookup at all in this case. So we can skip that method call, yes. So it's right here. When we look at the instruction sequences, we'll see at the top here, it's got this special instruction, opt-invoke delegate, opt-invoke built-in delegate. Don't worry. These toys are not for, today they're for us. But you can't call this in your Rails application, so don't worry about it. It's our secret in this conference. So I want to walk through the instructions for this method now. Now it's working, okay? I want to walk through the instruction sequences. So this is what the instruction sequences look like, and I just pulled it out of the new method here. The first thing that's going to happen, so we have our stack here on the right. As we know, we learned about the calling convention, so the stuff above the line is our parameters as well as any scratch space for locals. So we have a blank space for our one local variable obj, and we have one space for our triple dots. All right, so the first thing we do is we allocate an object. That's pretty clear. We call this RB class alloc. It pushes a new instance onto the stack. Then the next thing we have to do is, we set a local, that's assigning obj. So it pops the value off the stack and it writes it above that line. Well, the next thing we have to do is we have to do a get local because we're going to pass, we're going to call the method on obj. So we do a get local. It reads off the stack and pushes the instance onto the stack. Then we have to do another get local, and that's for our triple dot. So we push two things onto the stack. Next, we do our method call, which pops the two values, and it pushes the return value of initialize. So whatever was in your initialize method, the return value of that gets pushed onto the stack. And we have to ignore that value, because remember, we don't want anyone to see that. Nobody looks at that value. So we execute a pop instruction to just pop that value off. And then finally, we do a get local again, which gets our new instance. And then we have a leave instruction, and that returns our new instance value. Now, unfortunately, this is 8 instructions. It's a lot of instructions. And I wanted to do it in fewer instructions, so guess what? New primitives, yes. I added a primitive.pop. It does what it says. It just pops a value off the stack. I added another primitive.dupe. It just copies a value on the stack. So now the code is like this. We're going to walk through it again. It's very obvious Ruby code, right? We all know. You see this in your Rails apps all the time. So we'll create a new instance. We push the instance we copy the instance. So we'll just copy whatever value is on the stack. We dupe it. Then we call the initialize method, and that pops the object off the stack, and it pushes the initialize return value onto the stack. We don't care about that value, so we just use this pop method to pop it, and then finally we return. So we're able to get this down to only 6 instructions. So I think it's pretty good. So far it looks like this. These are all of our instructions. And you can see right here is our initialize. And I want to note here, we have an inline cache here. So as we talked about, inline caches, very normal, regular inline caches right there. Now, I think we could get this down to 4 instructions. We were taking the train from Warsaw down here, so I was doing some Ruby development on Rails. Yes. I wasn't able to get it there. I have an idea. I think we can get it down to 4 and possibly even maybe 2 or 3 instructions, but I wasn't able to do it. So let's talk about how it performs because we're nearly out of time. So let's start with our very, very easy benchmark first. So this case here, we saw earlier in earlier slides, when we do this pattern, we would get 2 allocations every time. Now it is only 1. So we only get 1 allocation when we're allocating with keyword arguments. Does anybody use keyword arguments? That's not a trick question. Yes, okay, good. Yes, thank you. It makes me feel good. If you weren't using them, it's not as fun. So here's a benchmark. I wrote a benchmark for this. This benchmark, what it does is it allocates 1,000 instances of foo, and it just does it like this thing repeats the call to foo 1,000 times. And the reason I did that is to amortize the cost of this benchmark. So we're saying, hey, I want to make the run method very expensive. That way we're not spending our time inside of the benchmarking framework itself. We just want to like make a slow method that allocates a bunch of stuff. So if we do that and compare Ruby implementations, Ruby 3.5 is 2 times faster than 3.4. So we can allocate 2 times faster in this case. Okay, clap for that. That's great. Yes, thank you. Okay. Now let's keep. We're gonna really analyze the shit out of this thing. What about a basic object? Like let's say we just do foo, and then we do foo.new repeated 1,000 times. We benchmark that. What happens in this case? Well, this is a sad case. Ruby 3.5 is 12% slower when we do that. I'm not excited about that. Now I thought to myself, what if we add an initialize method to foo? Like, what if you do this? Like, what does it look like? Let's compare that. Well, in this case, actually, Ruby 3.5 is 14% faster. Yes, that's very, 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 very strange. We should all be thinking about this. Why does it do this? I have some ideas. Let's chat about why it does it later. Come ask me what my opinion is. Now, what happens if we add 1 argument, then 2 arguments, then 3 arguments, et cetera, et cetera, et cetera? What does the performance look like in that case? This is just positional arguments. This is what it looks like. So this is a ratio. So there's no units. What we're saying is higher is better. Ruby 3.4 is always a 1. And then anything above 1 represents a performance increase. So you can see here that Ruby 3.5 is always faster, no matter how many arguments there are, as long as there's an initialize method. Now, these cases, these were always using the same object, same class over and over and over again. And as we talked about, there's an inline cache in there. What if their inline cache misses? Like, what is the difference in that case? So here we have another benchmark that's like, we're going to take foo and we're going to take bar, and we're just going to switch between them over and over and over so that there's never an inline cache hit. What is the difference there? I didn't make a graph of this because the performance is exactly the same. So Ruby 3.5 performs exactly the same speed as Ruby 3.4. Now, what about varying the number of keyword arguments? We saw it with 3 keyword arguments, but what if it's like 0, 1, 2, 3, et cetera, et cetera? So here's a graph of that. Again, this is a speed up ratio, so anything above 1 represents a speed up. And you can see as we increase the number of parameters to new, our gains over Ruby 3.4 grow and grow and grow. Now, of course, again, this is 100% cache hit. What if it's 0% cache hit? Like, what if it's the extreme opposite in the other direction? Graph looks like this. It's a little bit lower, but still you can see our performance always wins. So performance summary, if the class implements initialize, it's always faster. This is the only slow case. It's about 12% slower. I have to ask, though, like, do we need to speed that up? Does anybody write a class and then not put initialize in it and then call new on that? Like, is that a thing? I personally think no, because I think most classes, if you're going to do a class, you probably write an initialize. That said, people with micro benchmarks will complain about it, so I would like to figure out a way to make it faster. So let's wrap this up. We looked at class new, the C implementation. We looked at inline caches. We looked at calling conventions. We rewrote class new in Ruby and checked out its performance characteristics. We answered the question, like, how can Ruby be faster than C? I hope that this talk got you excited about Ruby internals, and I hope it got you excited about using Ruby itself. Thank you so much. I'm so happy to be here. Hello. Oh my gosh. Sorry. I didn't know we had time for Q&A. Do we want to do that?
Maybe 2 questions.
I would love to field questions about this. I am so interested in this topic. Yes.
Tush.
Yes. So the question was, I showed that there is a performance increase when there's keyword arguments. Is it also faster when there are positional arguments? And the answer is yes. I had a graph in there. Let me show you just if we have it. That's not me.
Yes, it's there. Yeah.
Is it there? Okay, let's rewind. Oh no, that's the wrong direction. Come on, Aaron, let's find the graph. It's right here. And this is positional. Oh, okay. Yep. So it's always faster with positional arguments, but I think it's just a constant time increase. I don't think we see like a growth increase like keyword arguments.
Anyone else?
Yes.
What about the time spent on the lookup of the method of primitive?
What is the time? So the question is, what about the time spent on the lookup of the call to primitive? That's a really good question. There is no time spent on that because what happens is when the Ruby compiler sees anything that's like primitive.blah, the compiler intercepts that, and it doesn't emit a method call in that case. It emits a special instruction. So let me find an example here. Let's see. Where was I doing it? Probably this one's good enough. Maybe. Yeah, okay. Okay, so for example, this example right here where we're doing primitive.rb class allocate, the compiler intercepts that and it emits a special instruction. And if we look at the instruction sequences that are emitted, it's this instruction right here. There's no method call in this case. It just allocates an object. So we don't have any method call overhead in that case.
Okay, the last one.
You mentioned that when we pass keywords arguments, and it has to sort them, it at least has to check them. So is there a very big gap between that when it doesn't have to sort? If we pass our keywords in order, is it better, much better?
Okay, so the question was when you have a method that's calling with keyword arguments, if you call with a different order, so it may have to reorder them depending on what the callee expects. Is it faster if we have a method call with the keyword arguments in the same order as the callee? Like, if there's no reordering going on, does it make a performance difference? Right?
I guess yes, but how much?
I don't know. I don't know. I think it's like we've looked at this a little bit because we have some ideas about speeding it up. Like on our team at work, we've talked about like different ways we can speed this up. I don't think there is any performance difference at the moment because if I remember correctly, we have to do essentially a linear scan every single time. So the cost is essentially the same whether they're in the same order or not. So it's always going to be O of number of arguments. I think.
But if you have to sort, you need to reorder.
Swap, yes. So there is some overhead there, yeah. I mean, there could be some overhead, but I don't know what the difference is. We were talking about, I don't know if I want to keep blabbing on, but we were talking about like seeing if we can figure out a way to detect cases where we don't need to reorder, or like, for example, when you have call sites, actually one thing that, where is it? One thing that Truffle Ruby was doing, we had folks working on the Truffle Ruby team, and one thing they were talking, oh my gosh, where is the example? Let's just go here. Okay, I don't know. When you call a method with keyword arguments, it's known statically. Because like if you look at the source code of your method call, it's always going to be, keyword A : blah, B : blah. So we know that from your source code there. And what we could do is cache the translation. So make that part of the call. It's like when we call from foo into bar, like when we're calling foo, we can look and say, okay, we had to do this particular reorder the first time. And then subsequent calls, we would know it's the same order. As long as the method cache is good, like as long as the cache is good, we don't need to actually think about what order it's in. We have that information cached already. Yep.
Okay,
All right.
thank you.